Hello, this is section 11.3. This section is in this section we're going to talk about applications, analysis of algorithm efficiency 1. This is section 11.3. In section 11.5, we are going to discuss efficiency, the second part of efficiency. Okay, that means blah 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 efficiency, the second part of this material. All right, so that is section 11.5. That's for your extra information. Let me keep it somewhere here. All right. This section 11.3 has two parts. Today we're going to cover the first part. In the next day class, we're going to discuss the second part. All right, let's go forward. First, I read this. This slide explains the history of algorithm efficiency. Starting in late 1940, a number of mathematicians and computer scientists contributed to developing formal techniques for analyzing computer algorithms. All right, there are several people contributed. You might know this person, Alan Turing. He is the most famous person in this field. All right, so he is considered to be the father of algorithm efficiencies. All right, so he contributed to this area a lot. He's a theoretical computer scientist and also an artificial intelligence person. All right, Alan Turing. So that's all about the history, and then this slide gives you the motivation. There are several searching algorithms in this chapter. One searching algorithm is called sequential searching algorithm. This slide explains how we discuss efficiency of sequential searching algorithm. Let me read this. The object of search algorithm is to hunt through an array of data in attempt to find a particular item X. So your target is to find this item X in the list. All right. In a sequential search, X is compared to the first item. First you compare this X with the first item, okay, and then to the second item, and then to the third, and so on. Okay, so you keep on comparing this X to that, this X to this to that, and keep on doing that. So that is known as a sequential search algorithm. Okay, such algorithms are called sequential search algorithms. The search is stopped if a match is found at any stage. On the other hand, if the entire array is processed without finding a match, then X is not in the array. That's simple, right? So if the algorithm couldn't find this match, the conclusion is that element is not in the array. All right. So since there are a lot of computer science students in this class, you can understand this. Let's say this array has these elements 7, 8, 3, 1, 2, and then you are searching for 4. Okay, you are searching for 4. let x equals 4. All right. Then what will happen is it will pass a null. Okay, this will pass an empty set for the search because you don't find x equals 4 in this list. All right. So whatever pass here should be a null. All right. So go forward. An example of sequential search algorithm is shown dramatically in figure 11.3.1. All right, now in this algorithm, you are searching for x. All right, so it has these elements. It has this first element, second, third, fourth, fifth, sixth, seventh. All right, now you just have given x to you. Now you just search whether the first element is x. All right, whether the first element is x. If no, then you move in that direction. Now you search the second element is x. No, then you move in that direction. And then check the third element is x. No, then move in that direction and keep on doing. Keep on doing. And here what happened is you found x equals 5, the fifth element. Okay, x equals fifth element. Then the answer is yes. Okay, then you go down. That is the end of the search. Okay, the searching algorithm will pass the corresponding location. All right, so this is a simple sequential search algorithm. Okay, so this is a sequential search algorithm. All right, just go to the next slide. Find best case, worst case, average case orders. Best case, worst case, average case orders for the sequential search algorithm from among the set of power functions. So you are using power functions here. All right, as you remember, power functions are like this. Give me a second. These are power functions. You have to use power functions to compute the orders. Let me color this in a different. That's special. You have to find orders. When I say orders, you know there are 3 order notations that we already discussed. There are 3 order notations. The first one is big O, and the other one is big omega, and then big theta. There are three order notations in general, but when we there are 3 order notations, that's for sure. But when we simply refer like order, that is this one. It is big theta. Why is big theta? You understood that in the last section. These are not accurate. Not accurate as big theta. Okay, these are not big O and big omega are not accurate like big theta. Because of that reason, from here onward, we use big theta. When we say order, it is actually big theta, not any other type. So this is what we are referring when we say order. It is big theta. Okay, so we don't use big O and big omega. We introduced big O and big omega in the previous section for you to know. Okay, that's just to know. But big theta is the most important order notation. All right, so go forward. Okay, this is the example 11.3.1. That's the solution of that. Now what you have is, you have this sequence. Okay, the sequence is this, A1 up to AN. You have to find item X. All right, the best case is this. The best case is x is in the first element. The best case, the algorithm requires only one comparison between x and the items in this. All right. It requires only one comparison between x. Require only one comparison. Okay. How that happen? One comparison means this occurs when x is the first item. If x is the first item, this is x, then you just compare the x with the first element, then the algorithm will stop. All right. Then the order of this one is just 1 because you had only one comparison. Okay. You had only one comparison, so the order is just 1. All right. Order is 1. So you have to use power functions for that. You have to use power functions for that. Okay, something like this. It's a power function. Of course, 1 is a power. You can represent 1 as n to the power 0. Okay, so this is a power function. N to the power 0 is a power function. It's a power function, all right? Good. So let's move to the next slide. Now let's consider the worst case. When the worst case happen, you just compare all the elements until the last one. You compare all the elements until the last one. So last one is the corresponding x. All right. So how many comparisons are here? There are n number of comparisons because there are n elements in this list. So there are n comparisons. So we write the order is just theta n. All right. Order is theta n. Now we have to consider an average case. Okay, average case is the element is in the middle. The element is in the middle. All right. So in that case you need this many comparisons, n over 2 comparisons. Okay, it doesn't matter n is odd or even. That doesn't matter. Don't mind whether n is even or odd. That doesn't matter. Okay, you need that many comparisons. So in that case, the order is again n. For that, the reason for that is, as you remember, we have learned a theorem. If the function give me a second. You have learned a theorem. That theorem says if your function is a polynomial, like it should be polynomial, like a m x n m a m minus 1 n m minus 1 blah 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 a 1 x that, then fn is theta of n m. Okay, we have learned. There is also theorem. This is a theorem. Theorem in section 11.2. There's a theorem like this in 11.2. All right. Thus, n over 2. Let me just separate. So this is the theorem. Thus, this is theta n. That's because of the theorem. All right, that's the worst case order. Okay, so that's an easy example. Let's move to the next slide. There are two aspects of algorithm efficiency. Those are important. The first aspect of the algorithm efficiency is the amount of time required to execute the algorithm. All right, the time required to execute the algorithm. And then next one is the amount of memory space needed when it is run. All right, so there are the two aspects, most important two aspects of algorithm efficiency. In this chapter, we introduce basic techniques for calculating time efficiency. Okay, we just work on time efficiency. We work on time efficiency. We do not work on memory efficiency. All right, so that is not included in this class. Similar techniques exist for calculating memory efficiency. All right, so keep that in mind. There are algorithms available for that, algorithms and techniques available to compute memory efficiency. Occasionally, one algorithm may make more efficient use of time but less efficient use of memory space than other, forcing a trade-off based on resources available to the user. All right, so you might be familiar with this issue. You are making algorithms in daily basis. Sometimes some algorithms need more memory, and sometimes the algorithm need more processing speed. All right, processing speed means it needs the algorithm needs more time to run. That is the processing speed. All right, so let me write this as extra information. Let's say your algorithm, okay, you have an algorithm. There are two cases. Let's consider the first case is it has many nested for loops. All right, the next case is it needs to compute inverse of a matrix. I'm sorry. This is case 1. The case 2 is requires an inverse of a big matrix. All right, so those are the two cases. In the first case, it requires many nested for loops. The next case is it requires an inverse of a big matrix. So in this case, the first case, what will happen is many for loops means it consumes time. Okay, it consumes time. It consumes more time. Thus, need more processing speed. In the second case, it consumes more memory. More memory, thus need more memory. Okay, there are two cases. One case is memory requirement. The other case is the processing speed requirement. All right, so this is good extra information for you. All right, so just go to the next slide. All right. So here I have a question. How can the efficiency of an algorithm be calculated? So this is the question everybody has. Okay, that's what we're going to learn in this section. How can the efficiency of an algorithm be computed? All right, so that's what we're going to learn. Just go to find the answer for that question gradually. So all these slides will explain how to find the answer for that. Let's go step by step. Okay, so this answer depends on several factors. One is the size of the set of data that is input to the algorithm. The one thing is the size of the data. Okay, the size of the data that's input to the algorithm. For example, it takes longer for a sort algorithm to process 1 million items than 100 items. That's something very intuitive, right? Anybody knows that. Consequently, the execution time of an algorithm is generally expressed as a function of its input size. All right, normal input size is n. That means number of data instances. Number of data instances, which is n. That is the input size. All right, input size. The analysis of an algorithm for time efficiency begins by trying to count the number of elementary operations. Keep that in mind. You are counting number of elementary operations. These elementary operations are add, summation, division, multiplication, subtraction, comparison. All right, so these are the elementary operations that we're going to learn very soon. The number of elementary operations that must be performed when the algorithm is executed with an input size n. All right, then you can discuss the best case, worst case, or the average case. All right, let's go to the next slide. For instance, to compare two algorithms for evaluating a polynomial. Let's say you are evaluating a polynomial. All right, evaluating polynomial means something like this. Let's say you are given this polynomial n square plus 2n plus 5. Evaluating this polynomial means you have to find evaluating means you have to find f of n when n equals some number, maybe n equals 5. Okay, when n equals some number, you have to find f of n. All right, so that means evaluating a polynomial. Evaluating a polynomial, the crucial issue is number of additions and multiplications. Okay, here the issue is that you have to compute number of additions and multiplications. That means f of 5 equals 5 square That means 5 square means multiplication, plus 2 times 5 again, that's multiplication. All right. So here two operations, here two operations, here just one operation. You have two operations each for the first two terms, and then adding part, you add everything together, okay, which is 20, this is 25 times 10 plus 5 here, all together another one operation, summation. Let me write the entire word, operation. All right. So there are altogether there are 2, 2, 1. There are 5 operations. There are 5 operations altogether. All right. So go forward. That means evaluating a polynomial. So you just consider additions and multiplications. Additions include actually subtraction too. When you say additions, this include summation, subtraction. When you say multiplication, this includes multiplication and division. Multiplication is also, you can consider multiplication as division, or division as multiplication. All right. So how? Like this. Let's say you just multiply a with b. This can be given like a divided by 1 over b. Okay, now you see multiplication and division can be interchange. All right, so they can be interchange. So that's why I'm telling, when it says multiplication, it includes the division too. All right. All right. Number 2 is to compare two algorithms for searching a list to find a particular element. The important distinction is the number of comparisons that are required. All right, we have seen this in the searching algorithm, in the previous searching algorithm. What you require is number of comparisons. If you search an element in an array, so that's all about number of comparisons. Okay, here it is addition and multiplication. If you just compare two algorithms, what I'm saying is searching list. Searching a list is actually computing how many number of comparisons are there. Okay, you understand first point and second point now. Let's move to the next part. As is common, we will classify the following elementary operations. Here I'm going to give you elementary operations: addition, subtraction, multiplication, division, and comparison, that are indicated explicitly in an if-then statement using one of the relational symbol. All right. So you can just do it by if and else statements. All right. Let's move to the next slide. When algorithms are implemented in a particular programming language and run on a particular computer, some operations are executed faster than others. And of course, there are differences in execution time from machine to machine. You know that, right? So there are some, if your machine is having having better performance. That means it has better RAM and processing speed, and cache memory and all. Then that computer performs well than a normal computer. All right. So there are trades off like that. All right. In certain practical situations, these factors are taken into account when deciding which algorithm or which machine is used to solve particular problem. Okay, as I explained you before, if your algorithm has more for loops, then it's better to find a computer with high processing speed. Okay, let's say your algorithm has algorithm requires to find an inverse of a matrix, then you need more memory. Okay. All right, as an example, let's say you have two algorithms. Algorithm 1, okay, this has many for loops. Okay, that's algorithm 1. And you have algorithm 2. Require to compute an inverse of a matrix. Okay, you have to compute the inverse of a matrix. So these are the two algorithms you have. You have two machines. This is machine 1. Machine 1 has more memory. And then you have machine 2, which has more processing speed. Okay, then you have to choose which one is which. So you have to give that job to that machine and this job to this machine. All right, so you can understand that and then go forward. In other cases, however, the machine is fixed. Normally we consider machine is fixed in general cases, and rough estimates are all that are needed to determine the clear superior of the algorithm over another. Okay, so you have to assume that the machine is fixed in general algorithm efficiency computations. That's so very important to consider that the machine is fixed. If the machine is fixed, then you have to find out the superiority of the algorithm. Okay, superiority of over the algorithm. All right. Since each elementary operation is executed in time no longer than the slowest, the time efficiency of an algorithm is approximated proportional to the number of elementary operations required to execute the algorithm. Alright, so we assume that each computer requires a specific time to perform one elementary operation. Okay, let's say it needs some time, maybe 1 microsecond. Let's say every machine, that's an assumption. We assume that every machine needs 1 microsecond to compute one elementary operation. So the efficiency of the algorithm is then be given as how many number of elementary operations is taken by each algorithm. Okay, so this is explained in that slide. And here we have an example. All right, in this example, We have to consider two algorithms A and B that we discussed early. Just go back. So we discussed about two algorithms A and B somewhere at the beginning. Where is that? Where's that? Oh yeah. Yeah, this part relates to the next example. Okay, this part relates to the next example. So go to the example. Consider two algorithms A and B are designed to do a certain job. Suppose that for an input size n, the number of elementary operations need to perform algorithm A is between 10 times n and 20 times n. That the algorithm B is between 2 times n square and 4 times n square. All right, because of these numbers you understand that algorithm A, order of algorithm A is theta n and algorithm B is theta n square. All right, so you know how it works, the or notation. That means you have to just bound the algorithm between these two numbers, like algorithm A, which is between 10n and 20n. That implies algorithm A is theta order, which is n, and then 2n square alg B 4n square, and then alg B is theta n square. Here n, there n, and there n. Here n square, there n square, there n square. All right, good. To compare the efficiency of A and B, let max A be the maximum number of operations needed to execute algorithm. That means max A is the maximum number of operations needed to execute algorithm A, and let min B be the minimum number of operations needed to execute algorithm B. All right, let me write just A here. Max A, maximum number of operations to algorithm A. Min B is minimum number of operations to algorithm B. All right. Then you can understand max A is 20n, min B is 2 times n square. Then go to the following table. This table explains the computational times for each algorithm with different input sizes. All right, so max A is 20n, min B is 2 times n square, and this gives the difference. If you have 100 data instances, 1000 data instances, so these are the corresponding values, and that is the difference, okay, which is close to 2 millions. This is close to 2 millions, and then this is the next input size, which is 10,000, and this is the difference, which is close to 200 millions. All right, in the next case, which is close to 2, give me a second, this is millions, billions, okay, okay, 2 billion. All right. So these are the corresponding differences. Now you see that when the input size is getting bigger, these numbers are getting huge. All right. So this is approximately equal to. So these numbers are getting huge. So let me read the content here. To accomplish a job with an input size 1 million, algorithm B requires almost 2 trillion more elementary operations than algorithm A. Oh, I just put numbers wrong, right? So let me check it. Yeah, that's correct. This is not 2 billion. This should be 2 trillions. Okay, 2 trillions. Right? It says to accomplish a job with input size 1 million, algorithm B requires almost 2 trillion more elementary operations than A. Right? You can see that for small input sizes, the difference is not big, but for big input sizes, the difference is huge. One way to look at this is that algorithm B has to perform 100,000 operations for each single operation performed by A. All right, that means you could just divide this by that, so you will get 100,000s. All right, so divide 2 triple 0 triple 0 triple 0 triple 0 divided by 20 triple 0 triple 0. So you can cancel these zeros by that by that, and then this equals it is just 100,000s. All right, which is right here. All right, you can understand that. Let's go to the next slide. Measuring efficiency of an algorithm. So this is the definition. Here you have the definition. This definition explains how to measure the efficiency of an algorithm. Let me read this. Suppose the number of elementary operations performed when A is executed for an input size of n depends on n alone and not on the nature of the input data. Say it equals fn. This is the first case. In the first case, input size is n. Most importantly, this depends on n alone and not the nature of the input data. Okay, let's assume that the nature of the input data is not a matter. It is not a matter, the nature of the input data. Okay, the nature is nature can be considered as, let me write the nature of data. It might be with the large values versus small values. Large values versus small values. All right. In the next case, it will be positive versus negatives. Positive versus, let's say, positive values versus negative values. Or maybe integers versus natural numbers, or maybe integers versus real numbers. Okay, so there are several such reasons. Those are called nature of data. Okay, so we do not care the nature of the data, we only care the input size. Okay, then it equals it equals f of n. If f of n is theta of g of n, we say that a is theta of gn. Okay, so this is the regular order notation that you have learned early. We denote that as this. All right, so you have to find function fn, and then you could just find function gn, which gives the order theta of the algorithm. And in the next case, which is different, suppose the number of elementary operations performed when A is executed for an input of size n depends on the nature of the data as well as on n. So now the nature is considered. Okay, the nature of the data is considered now. Now the scenario is different. There are two cases, first case and second case. In the first case, we discuss Bn be the minimum number of elementary operations required to execute A for all possible input size n. If Bn is theta of g of n, we say that in the best case, now we discuss the best case and worst case because we have to consider the nature of the data too. The best case A is that. The best case of A is theta of g of n. Or we can write the same thing as A has the best case of order that. Okay, then go to part B. Let Wn be the maximum number of elementary operations. This is minimum number of elementary operations. Now we have maximum number of elementary operations required to execute A for all possible input sizes of n. If Wn is theta of gn, we say that in the worst case, A is theta of gn, or maybe A has worst case order of that. So don't worry about this. I'm going to teach you those later. Okay, so the thing is, this is not required. This is not much required for this class. Not much required. Normally, we do not care the nature of the data. Okay, let me write like not much required. All right, this is not much required. Let's move to example so we can understand that very well. This is example 10.3.2. In this problem, you have to compute the algorithm efficiency. Let me read that. Compute the actual number of elementary operations. So the algorithm efficiency is computed as elementary operations. You have to compute number of elementary operations that are performed when the algorithm segment is executed. All right. In the part B, it says use the theorem on polynomial orders to find an order for the algorithm segment. All right. Let's do the problem here. So in this problem, it goes like I goes from 2, 3, 4, blah 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 n. So how many indexes are here? There are n minus 1 indexes here. Okay, it is not starting from 1, it's starting from 2. So there are n minus 1 indexes. For each index, you have to sum up two numbers and then multiply this with that. Okay, so there's one operation here, there's another operation here. So altogether, there are, inside the for loop, there are two operations. Okay, there are two operations inside the for loop. So the for loop runs for n minus 1 times. So the total number of operations equals 2 times n minus 1. All right, 2 times n minus 1. That means 2n minus 2. And then use the you have to use polynomial, the theorem that on polynomial orders to find the order of the algorithm. So I just wrote this theorem somewhere above. Yeah, this is the theorem. So let me copy this theorem. And then let me paste it there. Alright, so this is the theorem. This theorem says the order here is thus by the theorem the order is theta n. All right, so this is explained in the next slide. If you want more information, you could just read these. So this explains all the information. So this is the answer that I obtained here, and this is the order. Not that. And this gives number of operations. All right, so you could read the next paragraph if you want. Actually, I explain everything right here. All right, so go to the next slide. In the next slide, you are given another block of algorithm. Here you have to compute the same things. Compute the actual number of elementary operations that are performed when the algorithm segment is executed. And then part B, use the theorem on polynomial order to find an order for this algorithm segment. All right, so that's what you have to do. Let's go to the next slide. The next slide explains everything step by step. So this is the for loop here. First count how many times the for loop runs. Okay, how many times the for loop runs. Here, this for loop runs this many times. Okay, that for loop runs this many times. You have to actually subtract. You have to subtract n over 2 that from n and then add 1. So that many times the loop runs. Okay, that many times the loop run. As an example, let's say I go through 1, 2, 3, 4, 5. So how many times this run? How many times this run? You can simply compute like 5 minus 1 plus 1, which is 5. All right, so you can understand that. Example. So you have to add 1 actually. You have to add just 1. Okay, and you have to just add 1 to get the corresponding number of operations. See, plus 1. 5 minus 5 means the start. So the 5 means the end. And the 1 is the start. Okay, then you have to add 1. So that's right here. This is the start. So this is the end. And this is the start. All right, plus 1 times. Then n is even. What happened? If n is even, then this can be written down like that. You know this notation. This you are familiar with this notation. This means the flow notation. This is the flow notation. All right, that's the flow notation. That means if you have 2.5, the flow notation, this is just 2. If you have 3 flow notation, this is 3. It goes like that. Okay, if you have 7.8 flow notation, this is 7. All right, so this is clear to everybody. So that's the flow notation. If n is even, that means n is something like 2, 7, 2, 8, maybe 10, numbers like that. Then you can just flow notation if n is even. Wait a minute. N is even, n divided by 2 is an integer. So for that you can just replace n over 2. All right, so that's clear to you. Then this can be written down as that equals n plus 2 divided by 2. When n is odd, this is actually that. Okay, this is actually that. As an example, let me write an example for that. N is an odd number, let's say n is 5. Then n over 2 flow function equals 2.5 flow function equals 2, okay, which is same as n minus 1 over 2, which is 2. Okay, these two are equal, you can see. These, I'm sorry. These two are equal. Okay, that means these two equal to. All right, so that is given right here. And then you can replace this equation by that, by that, by that. Okay, this is simple algebraic simplification. Now you got two numbers. The first number is this. The other number is that. Okay, you got two numbers. When n is odd, you get this number. When n is even, you got that number. Okay, now go down. Now you have to compute the polynomial, the order of the polynomial. This is same. This is similar to half times n plus 1. This is similar to half times n plus 3 over 2. For both cases, you have only n here. Okay, so the order is theta n. All right, so that is by this theorem. Where's the theorem? Where's the theorem? Somehow the theorem was vanished. So let me copy the theorem again. Oh no, theorem is right here. By this theorem from section 11.2. All right, by this theorem. All right, that theorem is right there. By using this theorem, we say this is just order theta n, this is just order theta n. All right, so that is the end of the section. Thank you very much.